Hello students, good morning and welcome to another video lecture of physics. Now in this video lecture we are going to discuss about uniform circular motion. Now what do you mean by uniform circular motion? If an object is moving along a circular path with constant speed, remember for circular path velocity will never be constant, right? So if an object is moving along a circular path with constant speed, then such a motion of an object is said to be uniform circular motion. If an object is moving along a circular path with constant speed, then such a motion of an object is said to be uniform circular motion. Right, so this is the definition for uniform circular motion. If an object is moving along a circular path with constant speed, then such a motion of an object is said to be uniform circular motion. Remember, speed will be constant but velocity will be different. Magnitude of velocity is speed only, right? That is constant, but at each and every point its velocity will be different, and the direction of velocity can be obtained by drawing a tangent at a given point. Say for example, if an object is moving along this circular path, right? If this is the center O, let us say initially at time t equal to 0, particle is at point P. At time t is equal to 0, suppose at time t equal to 0, particle or an object is at point P, which is at a distance r1, right? Vector r1, position vector r1, right? And at that point its velocity is, let us say, v1. Its velocity will be tangent to that point, so its velocity here will be in this direction. Let us say this velocity is v1. After time t, suppose this particle moves to point q. At time t is equal to t, particle is at point q having position vector r2, right? So at this point, let us say its velocity will be v2. You have to draw tangent at a given point, so the direction of velocity will be this. Let us say this is velocity v2, and this angle is, let us say, delta theta. Now here you can see that r1 and r2 are radius of the circular path. R1 and R2 are radius of circular paths. Hence, we can say that their magnitude will be same, but their directions are different. Look, R1 is in this direction and R2 is in this direction. So, direction wise, R1 and R2 are different, but in magnitude, R1 will be equal to R2, that is equal to radius of that circular path. So, here what you have to write is, at time t equal to 0, suppose at time t is equal to 0, particle or an object, you can write, is at point P. It is at point P having position vector r1 and velocity v1, and at time t equal to t, and at time t is equal to t, this particle is at point q. This particle is at point q having position r2 2 and velocity v2. Now the most important thing is this radius and velocity will always be perpendicular to each other, right? If you draw this properly, then tangent to this point will be in this direction, right? So if you see, this angle will always be 90. Radius and velocity will always be perpendicular to each other, you can see, right? So radius and velocities are always perpendicular to each other. This point PQ will be delta R. PQ will be equal to delta R, which is actually R2 minus R1. Right. So if velocity is perpendicular to R, right, so V1 and V2, if you draw separately, let me draw first like this. Let us say this point is O, P, Q. Here we'll write point G. Look, V1 is in this direction. So this is vector V1. And V2 is in this direction. This is vector V2. And this will be delta V. Right. So you can clearly see that if this angle is delta theta, this will be delta theta. We can easily prove this, right? It is totally mathematical. Look, if R1 is perpendicular to V1, R2 is perpendicular to V2, then this angle and this angle will be same. You can easily prove that. Time being, we are not going to prove this, right? G, let us say this point is H and this point is I. So you can see that the change in velocity is acting towards the center of the circular path. The change in velocity is acting towards the center of the circular path. Or we know that change in velocity with respect to time is acceleration, and hence this acceleration is acting towards the center of the circular path, and it was given name by Newton as centripetal acceleration. The acceleration which is acting towards the center of a circular path is known as centripetal acceleration. Centripetal means towards the center, center seeking acceleration. It is a Greek word, right, which means that towards the center. So centripetal acceleration. So the acceleration here will be known as centripetal acceleration. Now look, if this angle is delta theta, this is delta theta, R1 and R2 are constant, V2 and V1 are constant. So triangle here, triangle OPQ and triangle GHI are similar triangles. You can easily prove that this angle will be delta theta, right? If you want, please tell me. We will discuss in one of our video lecture that how this angle is also delta theta. But for time being, remember this angle will also be delta theta. So these two triangles are similar triangle, and we know that for similar triangles, ratio of sides are always equal. So here you can say that, therefore, we can say that delta R over magnitude of R1 will be equal to, in magnitude, right? Ratio of sides are always in magnitude, direction is not necessary, will be equal to delta V over V1 in magnitude. You can also write V2 and R2 if you want. But here let us write here only. R1 will be equal to R2 equal to R in magnitude, right? Because that is radius of the circular path, right? So in magnitude both are same, and in the same way V1 will be equal to V2 equal to V, that is speed, which is constant. Look, speed of a particle along a circular path is always constant. That is why it is known as uniform circular motion, right? So speed which is constant. So V1 equal to V2 equal to V. So let us put R1 equal to R and V1 equal to V. So we'll get delta R over R will be equal to delta V over V. Right. So if you rearrange this term, delta V will be equal to V delta R by R. So if you divide both this side by delta T, right? So delta V over delta T will be equal to V by R into delta R by delta T. Now if you take delta T tends to 0, if we take delta T tends to 0, then delta V by delta T will be instantaneous acceleration, right? delta V by delta T can be written as, for delta T tends to 0, you can write the above equation as dV by dt is equal to V by R dr by dt. Now change in position with respect to time is velocity, and change in velocity with respect to time is acceleration. So therefore you can say that therefore dV by dt is acceleration A is equal to V by R into change in position with respect to time is again velocity into V. So this is A is equal to V square by R, and this A is represented by AC, where C represents centripetal acceleration. In some of the reference book they have written A perpendicular, right? That is centripetal acceleration. Perpendicular means it is towards the center and perpendicular to delta R. Look, delta V is also perpendicular to delta R. As R is perpendicular to V, delta R will be perpendicular to delta V, and that's why this is known as perpendicular acceleration or centripetal acceleration. So the formula for centripetal acceleration is AC is equal to V square by R, most important formula. Clear? So do one thing, pause this video and copy this first. Now we do have one more relation for centripetal acceleration, there is one more equation for centripetal acceleration, that is in terms of, you can say that, angular speed or angular velocity. So first of all, what is angular speed or angular velocity? Right, so for that we should know certain thing. You will come across this in chapter 7, rotational motion. So for that, let us say if an object is moving along a circular path or any random path, if an object is moving along a circular path, let us say here we have a particle at point P at time t is equal to 0. It is moving along a circular path like this, right? So let us say if you continue this, you will get a circular path, right? So let us say at time t is equal to t, particle moves to point Q in such a way that it has covered a distance of delta theta, right? This distance, angular distance, is known as angular displacement, right? Initially particle was at point P, it has moved to point Q, making an angle of delta theta. So this delta theta over here is known as angular displacement. This is angular displacement. We know that P and Q are displacement, right? Distance and displacement, and this is angular distance or angular displacement. And the time taken is, suppose if you write here t and here t plus delta t, then the time taken is delta t. Delta t is time taken to cover this angular distance, right? So here we can say that angular speed, its symbol is omega, which is defined as, look, what is speed? Distance upon time. So what is angular speed? Angular distance upon time, or angular velocity is angular displacement upon time. So here you can say that angular displacement upon time, that is delta theta by delta t. Again, if you take delta t tends to 0, that is limit delta t tends to 0, you can say that delta theta over delta t can be written as d theta by dt. Unit will be, angle is radian and time is second, so unit will be radian per second. So this is angular velocity, right? Omega, angular velocity, delta theta by delta t or d theta by dt. Now also we know that what is formula for arc. This all thing we are going to use, right? So what is angle? We know that angle equal to arc upon radius. Angle is equal to arc upon radius. So what will be arc? Arc will be angle into radius. So here arc is PQ, right? So arc PQ will be equal to, angle is delta theta into radius is suppose r. So delta theta into r. This equation and this equation you have to remember, right? This we are going to use now to derive another formula for centripetal acceleration. Now for that, again we will draw the same figure for UCM. UCM means uniform circular motion. Again we are going to draw the same figure, but this time I will change the position for P and P dash. Let us say this is center O, particle is at point P, particle is at point P at time t is equal to 0. It has moved to point Q. It has moved to point Q at time t is equal to t. So here velocity is in this direction, that is v1, and here velocity is in this direction, that is v2. So this will be the perpendicular distance between P and Q, that is delta r. Let us say this distance is r2, vector r2, and this is r1, what we have discussed initially, right? So this is perpendicular distance delta r from P to Q. If you draw perpendicular to delta r, if we draw perpendicular to delta r, we'll get delta v. So let us consider a point G over here. You can see that this is v1 and this is v2, vector v2, right? And this is delta v. Again, you can see that this delta v is acting towards the center, right? We have till this delta v is towards the center. Clear? If this angle is delta theta, again this angle will be delta theta only. Fine. Now we know that arc, here we have already written, right? Arc is angle into radius. We know that arc is angle into radius. So here angle is delta theta and radius we have taken as capital R. R1 we have assumed that R1 is equal to R2 and that is equal to R. So radius we have taken capital R, and here arc is PQ, distance PQ, right? If delta t is very small, if this time interval is very small, then in that case distance and displacement will be nearly same, that we have already discussed. Right, now what is the formula for velocity? We know that velocity is arc PQ upon time taken. Let us say time taken is delta t. So what is arc PQ? Delta theta by delta t into arc. Look, delta PQ is delta theta into r. So delta theta into r upon delta t. But delta theta by delta t, we have already seen delta theta by delta t is omega, angular speed. So you will get v is equal to omega r. This is again a most important relation, v is equal to omega r, where omega is angular velocity and r is radius of that circular path, and v is linear speed and angular speed. So you can say that this is relation between linear speed and angular speed. What is relation between angular speed and linear speed? Then you will write v is equal to omega r. Clear? Now centripetal acceleration is defined as, centripetal acceleration is v square by r. So v is omega r, so omega square r square by r. So one r will get cancelled out, so centripetal acceleration will be omega square r, where omega is angular speed. Now here we are going to define two more things which you have to remember. The first one is periodic time. What is periodic time? Its symbol is capital T. The time taken to complete, here only will write the time required to complete one revolution is known as periodic time T, and number of revolution per second is known as frequency. In textbook they have taken symbol nu, but we are going to write frequency as f. In textbook they have taken symbol like this, nu, but we are going to take symbol f, right? So therefore you can say that f equal to 1 by t. Now We know that velocity equal to, or speed is equal to distance over time taken. So for one complete rotation along the circular path, if you draw a circle over here, then for one complete rotation, the distance will be circumference. So here it will be 2 pi r and time taken is t. Right, so you can use v is equal to 2 pi r upon t, and 1 upon t is f also, so you can write 2 pi r f. So therefore centripetal acceleration, which is equal to v square by r, can be written as 2 is 4 pi square r square f by r, so 1 r will cancel out, so 4 pi square r f square actually, f square, so 4 pi square f square into r. This is another formula for centripetal acceleration. You have to remember all this formula, or else you can remember this main formula, and from this formula you can derive this, right? So this is the formula for centripetal acceleration. Do one thing, pause this video and copy this first. So for uniform circular motion, that is for UCM, the first thing is centripetal acceleration is v square by r, or centripetal acceleration is omega square r. Both this formula you have to remember. Omega is again 2 pi f, you can write. So centripetal acceleration will be equal to 4 pi square f square r. Right, so this is the formula for centripetal acceleration. All this formula you have to remember. The most important thing, note speed, that is you can say that magnitude of velocity and magnitude of acceleration for uniform circular motion is always constant. This is the condition for uniform circular motion, that is magnitude of velocity, that is speed, and magnitude of acceleration should always be constant. What will be the direction of centripetal acceleration? Centripetal acceleration is always acting towards the center of circular path. Right, centripetal acceleration is always acting towards the center of the circular path. Right, so its direction will keep on changing, that is magnitude remains same, but direction changes. How direction changes? Suppose if this is the circular path, right, and particle is at point P, then centripetal acceleration will be in this direction towards the center, right? If particle is at point Q, then acceleration will be in this direction. So obviously these two directions are not same. So magnitude will remain same, but direction changes. In the same way, the magnitude of velocity is always constant, but its direction is always perpendicular to radius of circular path, or you can say that, or it is tangential to the given point. Right, velocity will be always tangent to the given point. Suppose at point Q, what will be the direction of velocity? If it is moving in anti-clockwise direction, then velocity will be in this direction. For point P, if you draw a tangent, then velocity will be in this direction. Clear? Next, we are going to solve example based on this. Example 4.10. An insect trapped in a circular groove of radius 12 cm Radius r is given as 12 centimeter. Moves along the groove steadily at complete 7 revolution. It is moving along that groove continuously or constantly, steadily, and completes 7 revolution in 100 seconds. Number of revolution is 7 and time taken is 100 seconds. What is the angular speed and linear speed of the motion? We have to find angular speed and linear speed. So actually for angular speed is angular displacement upon time taken. So first thing which we have to calculate is angular speed and linear speed. So what is angular speed? Angular displacement for a circular path, right? The distance covered for one revolution is 2 pi. For a circular path, the distance covered for one revolution is 2 pi. So for n number of revolution, n into 2 pi by t. So here n is number of revolution is 7 into 2 into 3.14 by 100. So 7 into 2 into 3.14, if you multiply this, 7 into 2 is 14 into 3.14 divide by 100, you will get 0.43596 radian per second. If you want, you can nearly write this as 0.436 radian per second, right? Now for linear speed, we know that V is equal to omega r. Now omega is 0.436 into r is 12. So 0.436 into 12 will be 5.232. 5.232. This is in centimeters, so centimeter per second. So the linear speed is 232 centimeter per second, and that is 0.436 radian per second. B. Is the acceleration vector a constant vector? What is its magnitude? In B, it is given that is acceleration vector is constant. Answer is no, because we have already seen the magnitude of acceleration will remain constant, but its direction changes. So vector acceleration A vector is not constant because its direction keeps on changing. What is its magnitude? We have to find centripetal acceleration. Now if you want, you can use V square by R formula. If you want, you can use omega square R, whatever you want to use. Let us use V square by R. V is 5.232 whole square by R is 12. So that is equal to 5.232 whole square divided by 12 will be 2.281 centimeter per second square. This will be the answer for centripetal acceleration, 2.28. In textbook they have written 2.3 centimeter per second square, right? So they have round of this, so you can write this is nearly 2.3 centimeter per second square. It is not necessary that you have to convert this into this. If you write this, then also you'll get full marks for that. Clear? So this is it for today's video lecture. I think we do have one more video lecture. In that we'll solve the remaining examples from our exercise. In exercise there are 3 or 4 examples based on this formula which we will solve. Okay. So till then, keep on reading, keep on writing, and keep on preparing. Thank you.